Welcome everyone to this seminar. So this is organized by UNSW, the Maths and Stats School, but it's also joined on with the Statistics Across Campuses initiative that groups a few Australian universities. So today we have the pleasure to have David Haziza. So David is based at the University of Ottawa. He was previously a colleague of Pierre Lafay-de-Michaud, our colleague here in the stats department. And today, David is going to talk about multiply robust imputation procedures for treatment of item non-response in surveys. Thanks, David, for agreeing to give the talk, and the floor is yours.
Thank you very much, Boris. Thank you for your kind invitation. Hello, everyone. Good morning. So I will talk, as Boris mentioned, I will talk about the imputation in surveys. And this is a joint work with Sisha Chen from the University of Oklahoma. So my field of research is survey sampling. So I'm going to give first a background, a brief background about survey sampling, and then we'll talk about imputation for item non-response. Surveys, we know, are widely used by national statistical offices. For example, Statistics Canada or the Australian Bureau of Statistics. In the US, they have the US Census Bureau and the Bureau of Labor Statistics. And in surveys, the objective is to estimate what we call finite population parameters. So in surveys, we deal with finite population, which is different from classical statistics, where essentially the populations are infinite. In surveys, we have a finite population, so be the population of household in Canada, the population of businesses in Australia, for example, and we are trying to estimate some aspect of the finite population. And typical parameters could include population mean, population totals, population proportions. So those are fairly simple parameters. And in some other cases, we may be interested in more complex parameters, quantiles, indicators, and so on. So I'm going to give a background. So here we'll denote the finite population. This is the population under study, and CAPN will be the size of the population. And in a survey, we collect survey variables, and I will call these variables Y1, YP. So P could be variables, and in some surveys, health surveys, for example, it could be a few hundred variables. And so what I'm calling here the population matrix is the data we would collect if we conduct a census and everybody respond, everybody tell the truth. This is we would observe the true matrix, the P by N matrix, and if we do a census. Of course, we don't do a census; it's too costly. But this is what we would observe if we could do a census. And once we have this matrix, conceptual matrix, then we can define the concept of finite population parameter. A finite population parameter is any function of this matrix. So, for example, the mean of the variable yj is one function, one simple function of this matrix yu. But we could have means, totals, the correlation between two variables. All of these are of this matrix, this census population matrix. So we don't conduct census because it's too costly. We don't have the resources. So to estimate these finite population parameters, we were going to select a sample S of size n. And the way we select a sample in surveys is through a probability sampling, so which I'll define in next. So what we often have is an indicator. It's called the sample selection indicator, which is 1 if unit I is selected. So II is 1 if unit I is selected in the sample. So we can construct, so for all the population units, I can define a 0, 1 variable. So this population vector IU completely characterizes a sample. It's going to be a vector of 0 and 1, telling me clearly who is in the sample and who's not in the sample. Sampling. Now, before selecting the sample, we often use what we call auxiliary variables, which are called the head variables, are available prior to sampling. So our samples are often selected from sampling frames, and on this sampling frame, we have variables prior to sampling for all the population units. So this Z variable, so we have, let's say, Q variable. So we have a Q by N matrix. This is essentially the sampling frame. And these variables will be used to, for instance, stratify the population. So for example, if I have a frame of businesses, I know, for example, the type of industry on the frame. So I can partition the population, I can stratify the population into different industries. We could have the size of the business, we could have the province, geographic information, and so on. So we have the Z variables, and the design is the distribution of these vectors of these we account for Z stratify the population. Nice feature the survey statistician.
Sorry, David? Okay, guys, I
But then
think
we have,
David,
yes.
it seems that the bandwidth is not really good. Maybe turn your video off if you can. That might help.
Video off. Whoa.
Because I think so. It was choppy for me, and I'm guessing it was choppy for everyone.
Can you? Okay, but my camera is turned off, I think. Can you see my screen?
I can still see you, but frozen, and now I can't see. You can't see your screen anymore. I think you need to share it again.
Screen, entire screen. Hello.
Yeah, all good.
Do you see
Perfect. Yeah.
Okay, sorry. So I will start from the beginning. So the sample is selected according to a sampling design. And what is a sampling design? Is the distribution of the vector IU. So IU is a vector of 0 and 1s, conditional on ZU. So we account for the Z variable used to stratify the population. So the nice feature about the sampling design in surveys is that it's a distribution that completely, it's known. In fact, it's known, or at least we know the first two moments of the distribution. In other words, the sampling design is perfectly controlled. The way we select the sample is perfectly controlled by the survey statistician. And so basic sampling design include simple random sample without sampling without replacement. In practice, never use simple random sample with replacement. We always use some form of stratification. So within each stratum, we can select a simple random sample without replacement. Often we use more complex designs, such as multi-stage design that involves some clustering, or a multi-phase design where we select a sample into phases. But at the end of the day, we have a sample design. This is a distribution of this vector I. And the first moment of the distribution is important in survey sampling because the expectation of this vector IU is the vector of the inclusion probabilities. So the pi I. So pi I is the inclusion probability of unit I. It depends on ZU. So, but for simplicity, I'm just going to call it pi. So pi I is the probability of unit I being in the sample, and this is known without error prior to sampling, and this will be used in point estimation. Then we have the second moment of this sampling design of the distribution, and so this is the expectation of the IU transpose, and so this is a matrix, the n by n matrix, and this is the matrix of second order inclusion probabilities. So pi 1 2 is the probability that unit 1 and 2 belong together in the sample. Why do we need the pi ij's? Because we need that for variance estimation in surveys. Once we have a sampling design, we know the pi i's. Often we know the pi ij's. In some cases, we may not know the pi ij's, but I won't talk about this case. So we know the pi i's and pi ij's. And now the objective, I will talk about estimating the population total. If we want to estimate the population mean, we simply divide the population total by the population size, so Ty over cap n. This will be the population mean. So if we know how to estimate the total, we estimate the mean. And for now, I'm going to assume ideal conditions, so no non-sampling errors. So no non-response, no measurement errors, everybody respond, everybody tell the truth. And what we have available for us is the y variable. So I'm going to take one y variable. So y will be for a generic notation for survey variable. So the survey available for all the sample units. And in this ideal setup, we have a well-known estimator called the Horvitz-Thompson estimator, or often in causal inference it's called the inverse probability weighting estimator. So the Horvitz-Thompson estimator is the weighted sum over the sample, the y values, weighted by the inverse of the inclusion probabilities. So we're using the pi i's in order to construct this estimator. So we're using an aspect of the sampling design to construct an estimator of the population total. And I can write this also, this sum of S, I can write the sum over S as a sum over U. But then I'm going to incorporate this sample indicator, which is 1 if the unit is in the sample and 0 otherwise. And the reason we write the estimator like this is because we have to study the properties of this estimator. And to study the properties, so expectation and variance. In survey sampling, we first need to specify what is treated as fixed and what's random. And in survey sampling, the Z, so the design variables used to stratify the population, for example, are treated as fixed. Therefore, the pi i's are fixed because they're a function of the Z. But also, the Y variables, unlike in classical statistics, are treated as fixed. So what's random? The only thing left is II. So it's 1 if you're in the sample, 0. In other words, in survey sampling, the Y's are treated as fixed, and we take the expectation with respect to the sampling design. In other words, the I variable are random. And this is called a design-based approach in survey sampling. So if pi i's are strictly greater than 0 for all I, so nobody has a probability of 0, then we can show that the expectation of the Horvitz-Thompson is equal to the true population total. In other words, the Horvitz-Thompson is unbiased for the true total, regardless of the variable I'm trying to estimate. Y could be income, it could be number of employees, and so on. And the reason we are able to have a non-biasedness regardless of the variable we're trying to estimate is because we're using the sampling design, the 1 over pi I, in our estimator. Then we can derive for any sampling design the variance of this Horvitz-Thompson estimator under complete data. And so this is given by this expression here. The expression is not very important. The only thing that we can notice is that it depends on the pi i's and the pi ij's, the second order inclusion probabilities. Now this variance is unknown because the y's are only available for the population for the sample, and the sum are over U here. So we cannot compute the true variance. However, we can estimate this true variance if pi ij's if all the pi ij's are strictly greater than 0, this does not hold for all the sampling design. But if I have a sampling design for which pi ij is strictly greater than 0, then it's easy to construct a non-biased estimator of the true variance. So this is the unbiased estimator of the true variance. I'm not going to give too much details. And we can show that this estimator of the variance is unbiased for the true variance. Once we have a point estimator and a variance estimate, we can construct a confidence interval as usual based on the central limit theorem, which I'll mention in few seconds. Now, I just want to mention something. In survey sampling, when we do asymptotic, because we need a central limit theorem to justify this confidence interval, we have an issue. Is that in classical statistics, we often say n goes to infinity. But in survey sampling, this statement doesn't make sense because we have a finite population and small n cannot be larger than cap n. The population size is finite. So what people did to study the consistency of point and variance estimator, central limit theorem, and so on, they had to define a new asymptotic framework. And essentially, the asymptotic framework assumes a sequence of finite population that are growing. And growing, in other words, we have a sequence of population larger and larger and larger, increasingly larger, so that cap n also goes to infinity. So in survey sampling, when we study the asymptotic properties of estimator, both small n and cap n go to infinity. So, and then we need some technical assumptions about, and I won't talk too much about it, but we have a technical assumption about the pi i's. We want them often bounded away from 0. We have some technical assumption about the pi ij's. We have some assumption about the second moment of the finite second moment in the population, and we can show that under this asymptotic framework, that the Horvitz-Simpson estimator is a consistent estimator of the true population total. If we want that the variance estimator, the estimate of the variance is a consistent estimator of the true variance, we need some additional assumption, something about the pi ij's and the fourth moment of the population. So and for the central limit theorem, in fact, it took a while before having a central limit theorem in the finite population context. I think the first one was Hayek in 1960, who proved the CLT for simple random sampling without replacement, and then he also did he had a result for Poisson sampling. And then slowly in 1985, then we had a result for Stratify SRS, proportional to size sampling, two-phase sampling. So it took a while before having a central limit theorem because of this unique asymptotic framework. But so people have shown this, so we can construct. We have a Horvitz-Simpson, which is a consistent estimator of the true total. We have a variance estimator, which is a consistent estimator of the true variance, and we have the central limit theorem. So we are fairly confident in ideal condition that we have a 95% confidence interval. So now I'm going to talk about non-response and going to imputation. This is the typical matrix data file that we collect in surveys. So we have our variables of interest. We have the individuals here, or the businesses. And we have three types of people. People who have responded to all the variables, so no issue. So this is the first set here. Then we have people who did not respond to anything. Why? Because we were not able to contact them, or because they refused to respond to the survey. So we have nothing for them. And this is called unit non-response. And then we have people in the middle for whom we have some variables, but not all. So they accepted to respond to some variables, but some variables are missing. And often the missing variable will be the sensitive question, income, or health questions. And the reason we distinguish item from unit non-response in surveys is because we don't treat the two non-response, the two types of non-response the same way. In fact, unit non-response is usually treated by some weight adjustment. So what is the idea about weight adjustment? In the file produced by Statistics Canada or the Australian Bureau, there is a column of weight. And what is the weight, WI? We can often interpret this weight, WI, as the number of people that unit I represent in the population. So for example, if unit 1 may represent 5 people, unit 2 may represent 10 people in the population, and unit N may represent 2 people in the population. The sum of the weights, so if we do the sum of the weights, it should be a pretty good idea about the population size. So this is the weight. So what we do for unit non-response, we simply eliminate these people from the file and then increase the weight of the respondent to compensate for the elimination of the non-respondent. So this is the treatment for unit non-response. So it's a weight adjustment procedure. So I'm not going to talk about this. I'm going to talk about the treatment of item non-response. So item non-response is we have holes here, and what we're going to impute for the holes. And very often, in most cases in practice, we use single imputation. So each hole is replaced. Each missing value is replaced by a single imputed value. We have also multiple imputation, but multiple imputation has a few issues, practical issues. Sometimes the files are very large, so often data users are not used to work with multiple files. But also there are some theoretical issues with multiple imputation in the context of surveys. So I won't talk about this. I'm going to talk about single imputation. So why do we do imputation? Because non-response has bad effects on the estimate. The main one is the non-response bias, which is if we don't do anything for non-response, if we don't adjust, so if we take the mean of the respondent, typically it will be biased because respondent and non-respondent do not share the same characteristic with respect to the variable we're trying to measure. So this is the first effect of non-response. The second effect of non-response is that because the sample size is smaller than expected, we selected the sample of size 1,000. At the end, we ended up with 500 people. So because the sample size is smaller, we know that the variance of the estimator will be larger. And this additional variance is called the non-response variance. And so when we estimate the variance in the presence of non-response, we have to estimate the total variance, the sampling variance that comes from the sampling process, plus the non-response variance that comes from the fact that some people did not respond. But the main objective of all the methods, weighting or imputation, is to reduce the non-response bias. So our first goal, and this is what I'm going to explain about imputation. So we do imputation to reduce the bias. So now we're trying to estimate the population total, and now we have some non-response to the y variable. So some y values are missing. So so suppose I will impute the missing values. So what is the estimator after imputation? The estimator of the total of the y's. It will be simply for the respondent. So Ri is 1 if unit I is a respondent. So he responded to the variable income. So let's take the income as as an example. So Ri is equal to 1 if income is available, and Ri is equal to 0 if income is not observed. So the first part here is the weighted sum for the respondent of the observed income. And for the non-respondent, 1 minus Ri, we use yi star. So yi star is the imputed value that will replace the missing yi. So essentially, the estimator after imputation is simply the weighted sum of this. So it's the Horvitz-Thompson type estimator of a variable which I call yi tilde, which is y if y is available, and yi star if y is not available and imputed. So this is the estimator after imputation. Just for some notation, because we need later, SR and SM. SR is the set of respondent to the y variable, so people who've responded to income, and SM is set of missing, set of non-respondent to the variable income. So after imputation, this is what the file looks like. So I have the column of income, and this column of income contains either observed values or imputed values. And essentially, this is a nice feature because then data users they can simply use complete data estimation procedures to estimate the total of the variable after imputation. They will simply apply these weights to the variable yi tilde, and this is what I had here. So we don't need special point estimation procedure. We can do as if the input values were observed values. For point estimation, this is not true for variance estimation. So now, how do we impute? So how do we create the yi star? So we have to make some assumption about the relationship between y, the variable requiring imputation, and x. Here, x is a set of fully observed variables. So fully observed variables means that it's available for both respondents and non-respondents. So y is missing, but x is not missing. And we have the usual assumption about that. We can allow some heteroscedasticity, but we assume that ci is a known coefficient. If ci is equal to 1, we go back to the normal homoscedastic model. So in the context of imputation, this model is called an imputation model or an outcome regression model. And what will be important is so we have the first moment of the model, expectation of y given x, and then we have also the second moment of the model, the variance structure. And note that we don't need to make any distributional assumption about the distribution of the errors. We don't need to say that the errors are normal or anything like this. So we just make assumption about the first two moments of the imputation model. I'm going to assume that the data are missing at random. So which means that essentially that after conditioning on x, okay, after accounting for x in the model, essentially what we're saying is that the distribution of income among the respondent is the same as the distribution of income among the non-respondent. Of course, this is a strong assumption. It may not hold. We cannot test that because we don't have the y values for the non-respondent. But if this is true, then because the two distributions are the same, then we can safely generate the imputed values from the respondent and then impute the non-respondent using this imputed values. So here what we have, so the probability of response, probability of Ri is equal to 1, only depends on xi. It doesn't depend on y after conditioning on x. And this probability of response, so the probability of response is a function of x. So this here will be called, it's an unknown function, and this is called the non-response model. So the non-response model is a set of assumptions about the non-response mechanism, the 0-1, response, non-response. So essentially we have two models. We have the imputation model for the y variable I'm trying to impute, and we have the non-response model for the probability of response to the income. And so typically what is being done in practice, there are many types of imputation, but I'm going to focus on semi-parametric imputation. The idea is to say, okay, y and x for the respondent. So based on y and x for the respondent, I'm going to estimate the beta coefficient, for example, by solving this estimating equation. I'm going to get this beta at r based on the respondent, and then we can easily construct the imputed values. So the predicted values. We can also use, often we use random imputation methods, so we add a residual. So I won't talk about this, we can easily extend to random imputation. I'm just going to consider this type of imputation. And the imputed estimator after imputation is the weighted sum of observed values, and for the missing values, we have our imputed values. So what are the properties of this estimator? Well, we can always write this. We can always write that the estimator after imputation, so t hat y, is equal to the complete data, so the Horvitz-Thompson type estimator, which we know is unbiased, plus this weighted sum of the residuals for the non-respondent, 1 minus Ri. So essentially what we can see, this is not rigorous, but we can see that if on average, we have the residual are equal to 0. So if the first moment of the model is correctly specified, then we can say that this estimator after imputation will exhibit a small bias or no bias. So the bias of the imputed estimator depends only on the first moment of the model. This is what we need to specify correctly to be able to achieve a non-biased estimator under the MAR assumption. If the first moment of the model is not correctly specified, then the estimator could be significantly biased. So essentially what I'm trying to say is that the point estimators are vulnerable to model misspecification. And the question is, since we are essentially vulnerable to model misspecification, can we add some protection? And the answer is yes. And this is, now I can talk about multiply robust imputation procedures. So in multiply robust imputation procedure, what we're going to do, instead of here, we just fitted, here we fitted only a single model. These values were obtained by fitting a model between y and x based on the respondents. And that's it. And this is usually what we do in practice. Not what we say is that instead of fitting one single imputation model, why can't we fit multiple imputation models and or multiple non-response model? So we can fit multiple models for y and multiple models for the probability of response, because we have the model for y and the model for the probability of response. And each model may be based on different functional and different set of predictors. So we may have a different m function and different x vectors for each model. And so what we want to do, we want to develop an imputation procedure that combines the information contained in all these models. So I still want to impute a missing value by one single imputed value, but I want the single imputed value to account for all the information contained in all these models. And what is a multiply robust procedure? A procedure is said to be multiply robust if the resulting imputed estimator is consistent if all the models but one are misspecified. So for example, if I fit 5 imputation model and 5 non-response model, my estimator will be consistent if out of the total of 10 models, 1 is correctly specified. So this nice concept was introduced by Han and Wang in 2013, and it can be viewed as an extension of the double robustness procedure. So in double robustness, what we fit 1 imputation model and 1 non-response model. So it's attractive because it provides some protection against model misspecification. So the question is, when multiply robust procedure could be useful? Well, for example, when we have a large number of predictors. So if we have a large number of predictors, we can use some variable selection. But depending on the method we're going to use or the threshold we're going to set, we may end up with different models. So what we're saying here is, instead of choosing one of the models, maybe I've performed 5 different variable selection methods, then I ended up with reasonable models. Then we can use the 5 reasonable models instead of choosing one among the 5 reasonable models. So that's one potential use of multiply robust procedure. Another thing where it can be useful to use multiply robust procedure is often people transform the data prior to imputation to remedy issues such as skewness, nonlinearity, or unequal variances. So there is some literature on transformation in the context of imputation. The question is how to choose a proper transformation. So choosing one transformation among several transformations is not always easy unless the sample size is very large. There's a paper by Christian Léger and Romano. So here what we say is that instead of choosing one transformation, we can choose 3-4, so we can have 3-4 models, each based on a different transformation, and use all these models to construct our imputed value. So we don't have to make a choice between the 3 or 4 potential transformations. So now I'm going to describe the multiply robust imputation procedure. So we have 2 classes of models. We have J non-response model. So those models are the models about the response indicator. So we're trying to model the 0, 1. Did I respond to the income or I did not respond to the income? And then we have the imputation model here, which are the models for the income variable. So we have J non-response model, K cap K outcome regression model or imputation model for the Y variables. So overall, we have K plus model. So the first step in multiply robust imputation is to first estimate, as usual, by maximum likelihood or by least square estimators, the alpha J, the alpha parameters here that we have here, and the beta parameters we have. So for each model, if I have 5 non-response model and 5 imputation model, then I have to estimate for each of these models the alpha and beta parameters. And we do that as usual, for example, by solving these estimating equations. So once we have the alpha and the beta, so now what do we have? So I constructed this table to make it clear. So we have unit 1. So unit 1 is a respondent. R is equal to 1. So no problem. We don't need to impute. But unit 2 here is a non-respondent. So this is why we need to construct the imputed values. So what do I have for unit 2? I have 5, or J, but let's say I have 5 estimates of its response probability to the variable income. 5 estimates based on 5 different models. And I have, let's say, 5 prediction of its income based on 5 different models for income. So what we want to do, so essentially we have 10 estimate overall prediction. So what we want to do is we want to combine for unit 2 all this information to construct my imputed value y2 star. So that's the idea about multiply robust imputation. So how do we do that? How do we combine this information? So we have 2 steps for constructing the imputed values. The first step is a compressing step. In other words, what we're going to do, we're going to compress the information included in the J non-response model and the K imputation model. So first, what we're going to do, we're going to create one single score that compresses the information in the estimate of the probability of response. So we'll call this PI hat. And then we're going to compress all the information contained in the outcome regression, in the 5 imputation models. And we'll call this score MI hat. And I'll show in the next slide how to do that. And once we have these compressed scores, then we'll use the compressed score to build the imputed values. Then we'll impute the value. So first step, compressing information. Second step, we'll simply do a linear regression. So the implementation step is just done by linear regression. So the question, how do we do the first step? How do we compress the information? I want to mention, if J is equal to 0 and K is equal to 1, this is the customary, so we have no non-response model, we have one single imputation model. If J is equal to 1 and K is equal to 1, this is what we call doubly robust imputation procedure, where we have one single imputation model and a single non-response model. So there are a few ways to compress the information. I'm going to present one, is through calibration. So calibration, it's related to model calibration, is something which there is a paper by David and Sarandon in 1992 in JASA. It's probably one of the most important papers in survey sampling in the last 40 years, because calibration is often used in practice. So what's the idea here? We are going to define some constraints, calibration constraints. The first constraint is about the population size. So we have the set of respondents. This is here the set of respondents, and this is the full sample. Remember that the sum of the weight is a good estimate of the population size. So I want to define, the idea is to create new weights. These new weights will be called WI tilde. The weights, the original weights, we defined this before, which is 1 over pi I, is WI. So what we want to do is we want to create new weights, which we call wi tilde, but we want these weights to satisfy the number of constraints. The first constraint is that when we apply these weights to the respondents, we want these weights, the sum of these weights, to still be a good estimate of the population size, which is natural. The second, I'll start with the third constraint. The third constraint is that we want that the sum, the weighted sum among the respondent of these new weights, the prediction, so we have K constraint because we have K imputation model. We've assumed K models for income. So essentially, this is the prediction of income based on the case model. So we want the weighted sum of the prediction to match the full sample estimate of the prediction weighted by the original weight. So what is the idea behind this? Why do we do that? The idea is to say, okay, suppose that we did not have any missing values. Suppose we observe the Y values. So let's replace the prediction by the true Ys. So I'm going, let's say the true income. What we have here is the usual Horvitz-Thompson estimator. And what we know about the Horvitz-Thompson estimator is that it is unbiased. So what I want to do, I want the respondent to match something that is unbiased. Of course, here in non-response situation, we don't have the YIs, but we replace the YIs by some predictions based on different models. And so that's the idea. So we want to force the respondent to match the full sample characteristics of prediction in terms of prediction. And we do that. We do that also here with the probability, the estimate of the probability of response. So we have J constraint because we have J models, and we have K constraint here because we have K non-response. So overall, we have K plus J plus 1 constraint. So essentially, what we're trying to do here in this K plus J plus 1 constraint is the set of respondents, because non-response is often a distortion of the original sample. So this constraint, the idea is, the rationale behind this constraint is to repair the distortion created by non-response. So those are the calibration constraints. And now what we want to do is we want to find these new weights, because that's what we want to do, as close as possible to the original weight. So we have to define a distance. There are a measure of distance between the new weights and the original weights, 1 over pi I. And there are many distance functions that we can use. I give here 3 examples. There are other examples. But essentially what we want to do is we want to find new weights so that the sum of the distances is minimized subject to the calibration constraint. So we want these new weights to satisfy all these J plus K plus 1 calibration constraint, this repairing the distortion. And so this, we know how to do that. This is a standard calibration problem in survey sampling. And the new weights, in fact, these new weights are, we can show that this is the product of the original weight, so 1 over pi I, times this calibration factor. Now this calibration factor, so this f function here, there is an f function, it depends on the g function we're going to use here. So we have multiple we can use the generalized chi-squared distance, for example, or the pseudo-empirical likelihood distance, and so on. So depending on the g function we're going to use, we're going to end up with a different f function. So I'm going to show that in the next slide. So this is called the calibration factor, and this factor it can be viewed as a summary of all the information contained in the J plus K plus 1 model. In the J plus K model, we have J plus K model. Why? Because this f factor here, this fi hat factor, depends on all the. Here we have an hi vector. This hi vector, you can view that as the vector where we stack all the prediction in some sense, or a function of the prediction. So this factor really can be viewed as a summary of all the information contained in the K outcome regression model and the J non-response model. So this weight here can be viewed as a compressed score that contains all the information that we find in all the models. Once we have, so this is an example. Depending on the G function we are going to use. So if we have 3 possible G function. Depending on the G function, we can see that we have different form of the weights. It's always the original weight times an adjustment factor, a calibration factor, but the calibration factor is different from one distance to another. So once we have these weights, so we choose a distance function. So we end up, let's say, with this. It's called a linear method because the calibration factor is 1 plus lambda hat hi. And I didn't say that, but this lambda hat, which is here, we want to minimize because we want to minimize the distance subject to j plus k plus 1 calibration constant. So the lambda hat it's essentially a vector of Lagrange multipliers of size j plus k plus 1 because we have j plus k plus 1 constraints. And then once we have these weights, so let's say we use this method, we have these weights. Now what we're going to do, now we're going to implement. Now I'm going to, so this is the second step. Second step is the implementation. We're going to do a linear regression with y as the dependent variable and hi. So hi is the vector that contains all the prediction that come from all the models. Their mean. This is just some details, but it doesn't really matter. But essentially, it contains all the estimate for the response probability and all the prediction for the income. And so we're going to do a linear regression with y as a dependent variable, hi as the set of predictors. And we are going to do a weighted regression, weighted by this factor fi hat minus 1. So here you can recognize the usual regression coefficient of a linear regression, but a weighted linear regression with weights. So the weights here are the wi, the original weight, times, and this is more important, fi hat minus 1. So at the end of the day, what we can see is this imputed values contains all the information that comes from all the models. Why? Because this fi hat and this hi contain the information that comes from all the models. So yi star is a prediction that combines all the prediction that comes from all the k plus j models. And once we have this imputed value, then we can construct our imputed estimator. As usual, it's a weighted sum of the y values for the respondent. And for the non-respondent, we simply impute this prediction. This is what we impute here that contains this compressed score, a compressed imputed value that contains all the information. And what we can show is that if one of the if one of the imputation model is true, then we can show that the multiply robust estimator is a consistent estimator of the true total and remember, as n, small n, and cap n go to infinity. So under this asymptotic framework in survey sampling. And if one of the non-response model is true, then this estimator is consistent for the true total, once again, as n and cap n go to infinity, which means that at the end, when we combine both theorems, then we have that the estimator is multiply robust. In other words, it is consistent, it remains consistent if one of the k plus j model is correctly specified. So this is the multiply robust property. So I'm going to show some simulation results. So we use the famous setup of Kang and Sheffer, who criticized the doubly robust procedure. So the famous paper with discussion, I think. So we use the same setup. So we generated 1,000 finite population of size 10,000. So here we are in the finite population setup. So we first created 1,000 finite population, and we used exactly the same variables, same models to create the population. So we had 4 x variables, and the y variable, let's say income, was related to x1, x2, x3, x4 through a linear model. And so we had 1,000 finite population, each of size 10,000. Here we have the 10,000 is the size of the population. And from each of the 1,000 populations, we selected, I will come back. We selected, so our goal is to estimate the population total. And from each population, we selected a sample of size n is equal to 800. We have other sizes in the paper, according to randomized systematic sampling with probability proportional to size. In other words, it doesn't really matter, but essentially the probability of being included in the sample is proportional to some size variable. So for example, in a farm survey, some farms are much larger than other farms. So a large farm will have a higher probability of inclusion. So this is called proportional to size sampling. So, so psi I here is the size variable, the size of the farm. Once we have selected our samples, then we generated non-response. So we generated the response indicators so that the probability of response, the true model, was, you can see the logistic model, the probability of response depends on x1, x2, x3, x4 through a logistic model. And we made sure that we had a response rate of 50%. I think in the paper we have 30% and 70% also. So once now we have created the missing values. So I just want to mention the true model for y is a linear model that depends on x1, x2, x3, x4. And the true model, the true response mechanism is a mechanism that also depends on x1, x2, x3, x4 through the function. And as in Kang and Schaeffer, we consider the following transformation, v1, v2, v3, v4, of the x variables. So essentially, they wanted to misspecify the models to see what will happen if the model were misspecified. And so they created some transformation of the x, and then they included this transformation in the model for the misspecified model. So to be clearer, here's the situation. So in our simulation, we assume 2 imputation model and 2 non-response model. So this model here is a linear model. That depend on x1, x2, x3, x4. So it's a correctly specified model. So we had the correctly specified model. This model is a logistic model based also on x4. So this model is the truth, and this model is the truth for the model. Then we have 2 more models, this one and this one. The first one is a linear model based on v1 to v4, so not the correct variable. So this is how we misspecify the model. So this is the misspecified, so this is the wrong model. And same thing here, misspecifying means using the v instead of the x, so this is the wrong. So we used 4 models overall, so k is equal to 2 and j is equal to 2, 1 true, 1 wrong on each side. And we computed several estimates of the form. So we imputed the variable using different imputation procedures. And then we computed the estimator of the total as usual. So this is the imputed value. And the way we obtain this imputed value, we obtain in different ways. First, we did some nearest neighbor imputation, the usual nearest neighbor imputation, based on the set of matching variable x, so the correct variable, x1, x2, x3, x4, and the incorrect variable v. We also computed doubly robust estimator, I'll come back to this, and 9 multiply robust estimators. We computed the Monte Carlo bias of estimators, and let's focus on the root mean squared error of the estimator. So Monte Carlo out of the 1,000 iterations. So here are the results. So first, I want to explain one thing, is that we have 4 digits. So for each digit, it's either 0 or 1. So the first 2 are the imputation model, and the outcome regression model for the y variable, and the last 2 are for the non-response model. So non-response model for the RI, for the probability of response. So this digit here means, so if we have a 1 here, it means that we use the true model. And if we have a 0 here, it means that we did not use the wrong model. So this is the true model, this is the wrong model. And 0, 1 means it tells me which models I used or did I use or I didn't use. And this is the same for the non-response model. So for example, here if we look at 1111, it means that we threw in all the models in the imputation. If we have here 1010, it means that the imputation was based on the true model, imputation model, and the true non-response model, whereas this one was based on the wrong imputation model and the wrong non-response model. So this is what we have. So if we look at the results, what we have. So first of all, the usual nearest neighbor. So nearest neighbor, sorry, it's the opposite. This is the imputation model. So sorry, this is the non-response model. So this is wrong. So this is the opposite. And this is the imputation model. So the first two digits are the non-response model, and the last two digits are the imputation model. So in nearest neighbor, we only have a model for the outcome for the variable y. So we have only one single imputation model, and 10 means we have the wrong we have the correct model. We have we did nearest neighbor based on x1, x2, x3, x4, and what we can see, bias is fairly low, 0.79, and RMSE is 2.19. When we use the incorrect model based on the v variable instead of the x variable, then we see there is a bias and much larger RMSE. There is no surprise. Then the next four estimators are I would say the customary doubly robust estimator. And we can see in the first three cases, at least one of the model is correctly specified. 1010, both models are correctly specified. 1001, only the non-response model is correctly specified. 0110, only the imputation model is correctly specified. And what we can see is that bias is very small and efficiency is pretty good for all the models. But then when we go to the last case, 0101, both models are misspecified. And here what we can see, there is a bias, and especially the efficiency here is bad. Sorry, 16 almost 17, which is very bad. So I'll come back to this in a few seconds. In the multiply robust, we have 9 multiply robust here. First, we said, okay, let's compute the 4 multiply robust using the technique I showed earlier, based on exactly the same model as the doubly robust estimator that have been proposed in the literature previously. And no surprise, when one of the model is correctly specified, at least one of the models is correctly specified, then we have essentially the same result as before. In other words, the same result here and here are the same. But what's interesting is that when we use this calibration way to compress the information, when we have 0101, so this is exactly the same as before, the doubly robust, the usual doubly robust, then we go from 16.8 to 3.05. So it's much stable. Still instant because both are incorrectly specified, but better numerical results. And these are 5 estimators where we use at least 3 models out of the 4. So in fact, in this case, we use the 4 models, and we can see there is the bias is negligible in all the cases, and efficiency is pretty good. And we can see that despite the fact that we've used 4 models here, the efficiency was not affected. And so since then we've done other simulation, and what we found is when K and J is reasonable, so when we have 5 imputation models and 5 non-response models, then the efficiency is not affected by the number of models. Of course, we have not tried if we had 50 models on one side and 50 on the other side. At some point, I think we'll pay the price. But if the number of models is reasonable, then we have pretty good result. And I'll just finish with one thing which is a bit surprising. Is the question is how? Suppose all the models are misspecified. So now I'm going to take a scenario where there is none of the model which is correctly specified. So first, I'm going to do an imputation based on P2 and M2. So what is P2 and M2? The non-response model based on the V and the imputation model based on the V. So both are wrong. I'm going to call this T hat Y MR1. Then I'm going to take another imputation procedure where still we have these 2 wrong models plus an additional wrong model that includes V1, V2, V3, V4, so it's wrong, plus all the interaction as the covariates. So here we have 3 models, all wrong. And then we have, again, always P2 and M2 with one additional model with a transformation of the V variable. So once again, there is no reason to do this transformation. The transformation is wrong. Then MR4 is the 3 models now, always P2 and M2, but with a third model, with another transformation, the log transformation. And we have a fifth imputation procedure where we have all these models. So we have P2, M2, one that includes V1, V2, V3, and all the interaction, and one with the transformation based on the square root, and one on the log transformation. So essentially, we have 5 models in the last imputation procedure. So, but they're all wrong. And what we can see, we see there is a bias, but we can see that the bias is not that large. And this result is when both models are misspecified. So this result here is nothing else than the result that we had here. Both models are misspecified. But what we can see is as we have different wrong models, especially the M5. M5 contains all the wrong models. It's inconsistent, but if we look at the RMSE, it's pretty good. We went from 3.05 to 1.92. So, and we've done that in a different. We did that in different empirical investigations, and the results are pretty consistent. In other words, multiply robust procedure, they tend to have good numerical performances compared to the usual, for example, doubly robust imputation procedure, even when all the models are misspecified. Of course, when all the models are misspecified, the estimator is inconsistent, but still, the behavior is not that bad, and we can see, for example, here. So I'm not going to talk about variance estimation, but we can estimate the variance of the multiply robust estimator. We can use estimator based on Taylor expansion. So it's a bit tedious because we have so many models, but we can have a Taylor expansion. And then we can use this estimator, which is essentially a complete data variance estimator, but instead of using the yi and yj, we have this variable that comes from linearization. And what we can show is that this estimator, this variance estimator, is consistent for the true variance, provided that the sampling fraction is negligible. So if the sample size is small compared to the population size, the interesting result is that this variance estimator is consistent for the true model, even if all the models are misspecified. Even if none of the model is correctly specified, this variance estimator, this V hat L, tracks the true variance. So at the end of the day, we can construct a confidence interval here, where we have here a multiply robust, we have a multiply robust imputation procedure, and if the sampling fraction is negligible, we have a consistent variance estimator. Therefore, the coverage rate will be close to 95% if all the models but one are misspecified. So we have not only multiply robust estimation, but multiply robust inference, because we are able to construct multiply robust confidence intervals in some sense. So we've done some extension about multiply robust multiple imputation and so on, fractional imputation. And we did also a multiply robust bootstrap for non-negligible sampling fraction. If the sampling fraction is non-negligible, here we have consistency if n over n is small. If n over n is small, then it's much more difficult. We can do some bootstrap, for example. So thank you very much.
Thanks, David. That was great. Great talk. I see we went a little bit over time, so we lost a few of the.
Sorry.
That's okay, no problem. So yeah, we lost a few people that probably had to go to meetings or to teach. But are there any, maybe one quick question for David? So I don't know if you can see, David, a few people say thanks in the chat.
Well, thank you very much for being here. Thank you.
Just one quick thing, I guess. So you were mentioning, all these techniques could be used for the Canadian Bureau of Statistics, or whatever it's called. Have
Statistics
you
Canada.
worked with them? Have you worked
Yeah,
with them, and
actually,
do they use these
yeah,
methods?
I'm a consultant at Statistics Canada, so I go once a week, and so we're trying to apply this kind of method to see what we obtain.
Okay, that's good. So it's used by the people who actually need it the most.
Well, we're starting to try to see if we can use it. Yeah.
Okay. And do you know if other institutions in different countries are using it?
Not to my knowledge,
Like,
it's fairly recent. So I don't think that people have started to use them,
not
if
yet.
they ever use.
All right. Well, thanks, David. Maybe are there
Thank you.
last chance for a question or comment? No. Okay. Well, thanks, David. That was
Thank you very
great.
much.
Thanks a lot for staying late to give
Yeah, no problem.
a talk. And I guess have a good evening then.
You too. Thank you very much.
Thank you.